two solutions, and it does a chemical reaction, and the chemical reaction is represented by a balanced chemical equation. And notice that for a lot of times these sort of calculations, we don't use molar masses because we get to moles just using volume and molarity. Okay, so let's see what this one is. All right. So what I like to do is I like to write underneath everything what I know. So it says, what concentration of H2SO4? So I find my H2SO4. Oh, did we already do this one? Yeah, we already we did this. We're ready for the third one. Yeah. Okay. All right. What concentration of Na2SO4? So that's sodium sulfate. So I'll write question mark molarity under my Na2SO4. Now, I'm given some information. See, with regard to the H2SO4, I'm going to write 25.0 milliliters, and then required 27.7 milliliters of 0.444 molar NaOH. So that volume and molarity goes with the NaOH. So I'm going to go 27.7 milliliters under NaOH and 0.444 molar under the NaOH also. So what do we know most about? Yep, we know NaOH, and I'm hoping you're getting into the pattern. We have the volume, we have the molarity, I can get to moles. So I'm just going to kind of put a moles here, moles of NaOH. Okay? So if I have moles of NaOH, I can use stoichiometry to get to the moles of Na2SO4, right? So I'm going to kind of draw a line here. I'm going to use stoich. I can get to, I guess I should say molarity. I can just get to moles. Moles of Na2SO4. Now, the only catch here, and we run into this a lot in this sort of problem, is do you see at this point I'm going to have moles. I know I can get to molarity if I take moles and divide it by volume, right? The volume at this point actually is 25 milliliters plus 27.7 milliliters. That's the number that's going to go in my divisor to knock out the molarity of Na2SO4. That's the only catch here. Because it's a titration. I mix these two liquids, two reactants, and I have a product, and I have moles. So that Na2SO4 is swimming around in this total volume. Yeah. It's kind of a common concept. All right, so here we go. So you guys said I know most about molarity, or most about NaOH. I'm going to start with, oh, wait a minute. Actually, where did this number came from? It came from Monday's. Yeah, Monday's lectures. So I'm not going to reinvent the wheel here. A few slides ago, we could use volume molarity to get to 0.0123 moles of NaOH. Now, I'm ready. I'm trying to get to moles of Na2SO4. What does that ratio look like?
1 Na2SO4 over 2 NaOH.
Yep. 1 mole Na2SO4 over 2 moles NaOH. Yep. So we can keep ourselves 3 sig figs, and you'll get 0.00615 moles of Na2SO4. So now we're over to the thing we're trying to get molarity of. So we can get molarity by taking moles divided by volume. So here we go.
Can you go back?
Yeah.
Okay, 1 second.
Just before the truth. Okay. So like I said, and it's kind of common in a titration to have like a couple different volumes. So I need to divide those moles by the total solution volume that Na2SO4 is swimming around in. So that's going to be my volume. So now don't make it more complicated than it is. I'm simply going to take those moles I came up with, the 0.00615 moles Na2SO4, divided by the total solution volume of the 2 reactants, 52.7 milliliters of solution. But that won't give me molarity. What do I gotta do? Multiply by 1,000 milliliters over 1 liter. Perfect. Yep. How many sig figs? 3. So like I've been saying, I probably would be equals 0.117 m Na2SO4. More explicitly, if we want to use that in a problem, it'd be 0.117 moles of Na2SO4 per liter of solution. That's kind of warm in here. I hope that cools it down, so we'll see.
And is that what's going to happen with most of those titration elements, that we have to find the total volume? So we have to add the volume of the reactants.
Your question is, so is that like a pattern for this sort of problem? Yeah. It's a pattern if you're trying to find the product. But remember, if we're trying to find the reactant, we just went with their individual volumes. So, yeah, yep. All right. So just a few general things about titrations. Now, every once in a while, so the test isn't made out yet, but on some of my tests, I kind of ask you questions about titrations in general. Remember a topic that we covered that I said sometimes I ask you questions about is yield. Why are yields generally low? Why is actual yield generally lower than theoretical yield? We have a whole lot of lists of questions or reasons, and then also kind of just the things about titrations. So all a titration is you're going to do tomorrow, it's quantitative, not qualitative, means you're going to get down to the nitty-gritty, quantitative and number about usually solution concentration. What you're going to see is we're going to use a burette, and we're going to let small amounts of, we call the titrant, into the reactant. So the reactant is going to be in a container, in our case tomorrow, an Erlenmeyer flask. So I'll show you what I mean. So this is a volumetric flask. Oh, sorry, my flask. Darn it. This is a burette. Sometimes it's spelled, I spell it both ways, a burette. This is the stopcock down here. This is actually what you turn to go ahead and let a small amount of liquid drip out. There are gradation markings here. They're kind of backwards. They start at 0 and they go down. This is a scary burette because actually the way the stopcock is oriented, if it's parallel to the tube, the stopcock is totally opened. So hopefully you don't have any solution in here. If it's perpendicular to the tube, that means it's all the way off. Anywhere kind of in between, perpendicular to parallel, it could be dripping a little bit. So there's basically kind of two things, kind of my up and down, that's my burette, that's my titrant. Down here, what I'm dripping it into, that's where my analyte's going to be. So here's a student doing this. Notice he's using a funnel up. No, I think it's an OpenStack. So I can tell it's an OpenStack.
Okay, never mind.
If I forget to tell you, I don't usually use a funnel, but you might want to use a funnel at the top there. And he's getting his burette ready. So this would be the titrant liquid, and down here would be the analyte. So I mentioned that the burette has gradations. Here's a close-up of the gradations, and I also mentioned that they're backwards. So the top gradation is going to be 0, and we're going to have you, like the slide says, when you get ready to write the raw data in your lab, in your notebooks, which everybody's going to bring tomorrow, right? Yes, everybody has their little notebook. Everybody fills out their own raw data with a pen. Anyway, this says that you're going to go to the nearest hundredth of a milliliter. So we've been talking about estimating between gradations. And if you're like me, a burette, since the gradations are backwards, I don't know, and estimating, it kind of drives me nuts. But I would get, to me, this is 2 mils, that's 1 mil. Okay, so this is B 1.5. I get about 1.62 milliliters. Okay, 1.62 milliliters would be what I have there. So let's take a quick look at this video. Possibility with regard to certain chemical reactions. First off, you saw 2 solutions. You saw a solution here, and you saw a solution here, the titrant and the analyte. They both have to, the reactants need to be able to dissolve into water, soluble, okay? Another thing is you're gonna see when we do calculations from a titration, information you get from a titration, we're gonna need to also use the balanced equation. So in our calculations, so we need the stoichiometry of the reaction. It needs to be fast. We kind of assume that reactions happen just like that, but not necessarily. Some of them can be quite long. So you can imagine if I'm dripping in titrant, okay, and it takes, if there's like a 1 minute delay, like for every titrant I add for it to react with my analyte, that's not practical. They need to find each other right away and react. The reaction needs to essentially go to completion. We've talked about reversible reactions in here, where instead of going from left to right, actually I have a 2-way reaction arrow. So they go from left to right, and they also go from right back to left again. If that's the case, your stoichiometry, it's just not going to work. Okay. And then the last one, and I kind of smile because this has probably gotten all chemists at one point, is that, remember the pink color we saw in the video? Yeah, the pink color only comes because they added probably phenolphthalein. They added an indicator, a third little harmless reactant that gives you color when you know that you've added enough titrant to use up all of your analyte. So you got to have something like that. That would be like a visual indicator, okay? But there are other ways to determine your endpoint. So the video talked about equivalence point. One of the things that tomorrow you're going to see how reproducible your titrations are. The equivalence point in the titration we saw with little pink color, I think your instructions for lab tomorrow is that pink color needs to persist for like 30 seconds or something, because eventually the pink color will go away. Too dark of a pink color means that you have over-titrated, and it happens. If you over-titrate, you're going to have to probably do a few extra runs. So just throwing that out there. Now there's a subtle difference between equivalence point and end point. Hopefully they're the same, like this slide says. The equivalence point is where the real chemistry is, where you've really, when you've dripped in your titrant, used up all your analyte, and the end point is what you see it as. So there might be a little bit of a difference, but hopefully they're the same. So I mentioned indicators. So we can, that pink color, that phenolphthalein, that's an indicator. And it smells really pretty good. Other ways of seeing that you're at the end point would be to just basically see what the conductivity of your solution is, potentiometrically. Okay, that's the same video. All right. So let's do an example problem with titrations. And it's going to feel very similar to the other solutions, stoichiometric calculations we've been doing. So I'm going to write underneath what we know. Wow, they had a big honkin' pipette. I said 10 mil, change that. They used a 50 mil pipette. We've got one. So that was the aliquot of acetic acid that they had down as their analyte. So I'm going to put 50.00 milliliters under my acetic acid, CH3COOH. And then I have the molarity of the NaOH, so I'm going to kind of put it on the second line under the NaOH. So I'll put 0.1150 molar. Like, dang, I don't know enough about either one of those to do a calculation, do I? But it's okay. So in the video we watched, that's what I kind of talked about in the previous video, but in the video we watched, if we were to rewind it, we would have seen that they started out, the initial, what we call the initial titration volume was 0.48 milliliters. They drifted to the end point, And then the NaOH, the final burette volume was 23.90 milliliters. Now, one of the things I'm going to tell you in pre-lab, or you'll read it in pre-lab, is for this particular type of titration, we don't start right at 0.00. Like, well, Mrs. Snipes, why don't you start at 0.000? 0.00. We just don't. So how can I get the amount of NaOH dispensed? Subtraction, exactly. So subtraction, that's all I'm going to do. So right here, I'm going to go ahead and I'm going to circle these two guys. And I'm going to put them up there because that's actually going to be my milliliters. So now I'm going to have milliliters of NaOH, molarity of NaOH. Can I get to moles of NaOH? Yes. So from these two, I can get to moles of NaOH. And from there, oh yeah, what was the question? It says using the information, find the, question mark, molarity under my CH3COOH. If I get the moles of NaOH, I can use stoichiometry to get to the moles of CH3COOH. Yep. Moles. Using stoich. And then we're kind of back to something we've done before. Once I have moles, and I know my aliquot volume was 50.00 milliliters, I can knock out molarity. That's it. So, let's see how this works. Yep, the analyte waiting down there in the Erlenmeyer flask was CH3COOH. The titrant was NaOH. You guys told me I can get the NaOH volume by difference, and I sure can. So 23.90 milliliters was the final volume, and the initial volume was, so we'll subtract from that, the initial volume 0.48 milliliters. And remember, we don't do as much subtraction or addition in this class, but if we do, we round according to decimals. So I know 2 decimals for both, so it gives me 23.42 milliliters. I'm going to run with that with regard to the moles of my NaOH now. So actually, what I like to do is start with that term now to get to moles of NaOH. So my first term, again, but no run-on equalities. So I'm going to rewrite that number, 23.42 milliliters of, it's going to be NaOH solution over 1. What do I have to do next? Get it to liters, yep. Take 1 liter over 1,000 milliliters. Yep, very good. Now I'm going to use molarity to get to moles. What does that look like? Do I use it 0.1150 or do I use it 1 over 0.1150? How many people think I use it just like that, the non-flip version? 0.1150. Yep. Yep. And then I'm going to carry my units though. I'm going to always unpack molarity. So that means 0.1150 moles NaOH over 1 liter solution. And then the beauty of that is my milliliters of solution cancel, my liters of solution cancel. I'm left with moles of NaOH. How many sig figs? 4. I'm liking 4. So for 4 sig figs, you're looking at 0.002693. And that would be units of moles of NaOH. And what did we say our last step was then? Yes, we have to do the stoichiometry. Very good. I'm going to rewrite this on the next slide. 0.002693 moles of NaOH. So I want moles of NaOH to cancel, and I want to be left with moles of CH3COOH. What does that look like?
1 mole of CH3COOH over 1 mole.
Perfect.
It's just the same.
It is just the same. And sometimes students will say, like, well, now why don't you even have to write that? Well, you do, because at this point, prior to that, if you don't do that, your units are moles of NaOH. You need moles of CH3COOH. Yep, so it's going to be the same number. So you're looking at 0.00 0.02693 moles of your CH3COOH. Looking good. So now what do I do with the number? I'm on my way to molarity.
Divide by volume.
Yep, divide by volume. And what was the volume? That's the volume done. 23 was the volume of the NaOH.
Oh, 50.
Yep, the volume of the CH3COOH was 50. Perfect. So you're looking at 0.002693 moles CH3COOH divided by 50.00 milliliters of solution. But that won't give us quite molarity, so what do we got to do to clean it up? Yeah, multiply by 1,000 milliliters of solution over 1 liter of solution. That should do it. 4 sig figs. And you're looking at 0.05387 m molar CH3COOH. Yeah, it's cooling down in here. Just in time for class to be over. All right, so yeah, so we're headed to the lab, and this Alta homework is going to be due Monday. I checked. But you guys